Introduction. The world around us is filled with connections. Social networks connect people, transportation networks connect cities, and the internet connects information. These connections can be modeled mathematically using graphs, which are powerful tools for representing relationships between objects. Graph coloring is a fundamental concept in graph theory that deals with assigning colors to the elements, vertices, of a graph, ensuring that no two connected elements share the same color. This seemingly simple problem has a multitude of applications and poses fascinating challenges that have captivated mathematicians for decades. The following is the importance of graph coloring. 1. Map coloring and cartography. Graph coloring ensures that adjacent regions on maps have distinct colors, improving visual clarity. 2. Task scheduling and timetabling. Graph coloring helps schedule classes, exams, and jobs efficiently by avoiding overlaps. 3. Wireless communication and channel allocation. Channels, colors, are allocated to devices to prevent interference in wireless networks. 4. Graph theory. Algorithms and optimization. Graph coloring problems inform algorithm development and optimization strategies. 5. Social network analysis. Assigning colors to nodes reveals patterns and communities in social networks. 6. Game theory and conflict resolution. Valid graph coloring models help resolve conflicts optimally. 2. Literature review. Graph coloring is a well-studied problem in graph theory and computer science. The key concepts and terminology include vertices, nodes, edges, the chromatic number, and etc. Here is an overview of key concepts and terminology related to graph coloring. Vertices, nodes. The fundamental units of a graph, represented as points or circles. In graph coloring, each vertex must be assigned a color. Edges. The connections between pairs of vertices in a graph, represented as lines. Two vertices connected by an edge are said to be adjacent. Graph. A mathematical structure composed of vertices and the edges that connect them. Graphs can be undirected, edges have no orientation, or directed, edges have a specified direction. Adjacent vertices. Two vertices are adjacent if they are connected by an edge. In graph coloring, adjacent vertices must be assigned different colors. Chromatic number, the minimum number of colors required to color all vertices of a graph such that no two adjacent vertices have the same color. Finding the chromatic number is the primary objective of the graph coloring problem. Proper coloring, an assignment of colors to vertices such that no two adjacent vertices share the same color is called a proper coloring. Click, a subset of vertices in a graph where every pair of vertices is connected by an edge. The chromatic number of a graph is at least as large as the number of vertices in its largest click. Independent set, a subset of vertices in a graph where no two vertices are adjacent. The chromatic number is also bounded below by the number of independent sets required to cover all vertices. Planar graph, a graph that can be drawn on a plane such that no edges cross. Planar graphs have important properties and applications, such as the famous four-color theorem for map coloring. NP-complete. Graph coloring is an NP-complete problem, meaning it is computationally difficult to find optimal solutions, especially for large graphs. This has motivated the development of approximation algorithms and heuristic approaches. 3. Applications. Graph coloring finds applications in numerous real-world scenarios, demonstrating its versatility and importance. Here are some real-world examples and use cases of graph coloring. 1. Scheduling and timetabling. Course timetabling, assigning courses to time slots and classrooms such that no student has conflicting schedules, can be modeled as a graph coloring problem, where vertices represent courses and edges connect courses that cannot be scheduled simultaneously. Sports scheduling, scheduling games or matches in tournaments such that no team plays two games at the same time, can be viewed as a graph coloring problem, where teams are vertices and edges connect teams that need to play against each other. 2. Map coloring. One of the classic applications of graph coloring is coloring geographical maps such that no two adjacent regions, countries, states, or counties have the same color. This problem has practical applications in cartography, political boundary delineation, and geographical information systems, GIS. 3. Computer networks. Channel assignment in wireless sensor networks, assigning communication channels to nodes in a wireless sensor network such that no two neighboring nodes use the same channel can be formulated as a graph coloring problem, where vertices represent nodes and edges connect nodes that are within communication range. Wavelength assignment in optical networks, assigning wavelengths to communication links in optical networks such that no two adjacent links use the same wavelength can be modeled as a graph coloring problem, where vertices represent links and edges connect links that share a common node. 4. Wireless communication and channel allocation. In wireless networks, graph coloring helps allocate channels to devices, such as mobile phones or Wi-Fi routers, to avoid interference. Each channel corresponds to a color, and adjacent devices, nodes, must use different colors to prevent signal overlap. 5. Graph theory. Algorithms and optimization. Graph coloring problems serve as a foundation for developing and analyzing algorithms. Researchers study properties of graph coloring, such as chromatic number and chromatic polynomial, to optimize solutions. IV discussions. Graph coloring is a fascinating topic in computer science and mathematics, with applications in various fields. Here are an in-depth comparison of some efficient graph coloring algorithms. 1. Greedy algorithm. Theoretical idea. Assign colors sequentially to vertices based on adjacency. Start with an arbitrary vertex and assign the first available color. For subsequent vertices, choose the lowest numbered color that doesn't conflict with adjacent vertices. Advantages. Simple and easy to implement, works well for many practical cases. Limitations. Not guaranteed to find the optimal solution, may use more colors than necessary, sensitive to vertex order. Optimality. Not optimal, but often close to optimal. 2. Backtracking. Algorithm. Theoretical idea. Explore all possible colorings recursively, backtrack when a conflict, same color for adjacent vertices, is encountered. Prune search space by considering constraints early. Advantages. Guarantees finding an optimal solution, if exhaustive search is feasible, can handle complex graphs. Limitations. Exponential time complexity, NP-complete problem, inefficient for large graphs. Optimality. Optimal, but computationally expensive. 3. Diez-Satter algorithm. Theoretical idea. Balances vertex degree and saturation, number of adjacent colored vertices. Start with an arbitrary vertex and assign the first available color. Choose the vertex with the highest saturation, ties broken by degree, for the next color assignment. Advantages. Often produces better results than greedy algorithm, balances color usage. Limitations. Still not guaranteed to find the optimal solution. Complexity lies between greedy and backtracking. Optimality. Not optimal, but better than greedy. Conclusion. Graph coloring is a fundamental concept in graph theory that involves assigning colors to the vertices, nodes of a graph, such that no two adjacent vertices share the same color. This seemingly simple problem has profound implications and a wide range of applications across various domains. The world around us is interconnected, with networks linking people, places, and information. Graphs provide a powerful mathematical framework to model and analyze these intricate connections. Graph coloring emerges as a crucial tool for optimizing resource allocation, scheduling tasks, and resolving conflicts within these networks. The significance of graph coloring spans diverse fields. In cartography, it ensures that adjacent regions on maps are distinguishable by color, enhancing visual clarity. In wireless communication networks, graph coloring algorithms allocate channels to devices, preventing interference and maximizing bandwidth utilization. Timetabling and scheduling applications, such as course scheduling and sports tournament planning, leverage graph coloring to avoid overlaps and conflicts. Graph coloring is a well-studied area, with key concepts like vertices, edges, chromatic numbers, and clicks forming the theoretical foundation. Despite its apparent simplicity, the graph coloring problem is computationally challenging, falling into the NP-complete category. This complexity has motivated the development of various algorithms and approximation techniques, each with its own strengths and limitations. Algorithms like the greedy approach, backtracking, and desatur strike a balance between efficiency and optimality, catering to different problem scales and constraints. The greedy algorithm offers a simple and practical solution, while backtracking guarantees optimal results at the cost of exponential time complexity. Desatur, a more advanced algorithm, often outperforms the greedy approach by considering vertex saturation and degree. As the world becomes increasingly interconnected, graph coloring remains a vital tool for optimizing networks, allocating resources, and resolving conflicts in a wide range of applications, from social network analysis to game theory and conflict resolution. Its theoretical depth and practical relevance continue to captivate researchers, driving the development of more sophisticated algorithms and fostering interdisciplinary collaborations.